Hi. You might notice I'm in a different spot today. It's really strange to be in the classroom talking to an empty classroom. Today's video is going to take us a step past proving triangles congruent. So in the last video we learned how to prove triangles congruent by three methods: side, 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 and angle, side, angle. But once we've proven triangles are congruent, what information can we draw from that? What further conclusions can we make? Well, this video is going to help you to understand what you can draw from triangle congruency and what's the justification for it. We're also going to take a look at circles and remind ourselves of some formulas we probably already know, but then also take a look at a new theorem. That's going to help us for the rest of the year. All right, I hope you enjoy the video and thanks for watching. Okay, so suppose we had already proven two triangles were congruent using side, 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 or side, or angle, side, angle. What then? What further conclusions could we draw? For instance, could we figure out whether angle C was congruent to angle Z? Well, you may remember from our sketch in the other video about the definition of congruent polygons that when two polygons or triangles are congruent, there are certain things that we know to be true simply by the definition. So we get a lot of information. If triangle ABC is congruent to XYZ, all the corresponding sides are congruent and all the corresponding angles are congruent. So that helps us with this theorem. We know that angle C would be congruent to angle Z because corresponding parts of congruent triangles are congruent, or we just write CPCTC. That means anytime you prove two triangles congruent, any of the 6 parts of the triangles can also be shown to be congruent by this new theorem, CPCTC. Okay, let's turn our attention to circles. You've probably been working with circles since the time you were in preschool, but really maybe haven't thought about exactly what a circle is. I always ask the class, is the circle a hula hoop or a frisbee? Well, the definition of a circle tells us that it's a set of points equidistant from a given point called the center. Okay, so if O is our center and A is on the circle is described by all the points like A that are the same distance away from O. What that means is our common conception of a circle is completely wrong. The area inside this ring, this green ring, is not the circle. Only the green ring is the circle. So, is a circle like a hula hoop or a frisbee? I hope you can see now, it's like a hula hoop. All right, OA is an important type of segment called a radius. And a radius is a segment drawn from the center of a circle to the circle. So AO here is drawn from the center, O, out to the circle A, and we call it a radius. Do you know that radii, which is the plural of radius, is one of the only words in the English language that has a double I? See if you can think of another one. Not Hawaii, though. Okay, let's reintroduce you to some formulas about circles you probably know. We may work with some problems involving area. That is the space inside the circle, and it's equal to pi times the radius squared. The circumference, you may recall, is the distance around the circle. So it's the distance that A would move as it started on the circle and came back to where it began. The perimeter of the circle, that's called circumference and equals 2 pi times the radius. Finally, the theorem is pretty straightforward and really very useful, and that is all radii of a circle are congruent. Unlike most of the theorems, it's not presented in conditional form. It's kind of like the theorem we just learned on vertical angles. So I hope you found this helpful to do the exercises in this section. If you still haven't figured out the word with double I in it, I'll be happy to tell you tomorrow. Okay, thanks for watching.